Tortured Numbers, a grower's guide to descriptive statistics. This is Jason DeVoe, application technology specialist with OMAFRA. A number of years ago, I was asked to write this presentation as growers were confronted with more and more graphs and tables and research results in meetings, and we're trying to sort of cut through the fluff to figure out what is it that the data actually tell us, what does the presenter want us to see, and what should we perhaps actually see. Ronald Harry Coase, an economist. You wouldn't think a statistician or a mathematician have a sense of humor, but they sure do. He coined the phrase, if you torture the data long enough, it will confess to anything. And I was first told this during my master's when I was going through a data set with one of my supervisors. And we weren't seeing what we really thought we were going to see from the data. And my supervisor said, well, we'll just change the statistic tests or the parameters that we're using until we do see the results we're looking for, which, by the way, is pretty unscrupulous and not the way science is supposed to happen. But it certainly shows that if you massage data long enough, you might get it to show anything you want it to show. Some of the easiest stats that we use and see day to day is descriptive statistics. And stats are just math tools. And like any tool, you need the right tool for the job. We use them to describe data. We also use them to find trends in that data against variation. And that just means, is what I'm seeing here real, or is it just a fluke? It helps us determine if a sample represents a population. In other words, is what I'm seeing here a special set of circumstances, or does it apply more broadly? And it lets us draw conclusions about that data. In other words, if I do all these same things all over again, will I get the same results or not? For example, in 1950, 25 university grads were asked what they earned in their first year of work. Here are their responses, and it's pretty much just a mishmash of numbers, isn't it? What can you learn from looking at these numbers? Well, you might be able to pick out a few things, but for the most part, it's a sort of confusing way to organize the data. So let's reorder them. Let's take that data set and list it from greatest to least, and we'll weight it. That shows how many times each value occurs. And here it is. Now, what does the data set tell you? Well, you can start to see a few things. The person who earned the most earned $45,000 a year, a pretty plum job, but the majority of students earned about $2,000. What would you say the average income is? Well, that's a little harder to figure out. So here's the first beware. The reported average might depend on what you're meant to see. There are three numbers that might be used as an average. The one we're most familiar with is the mean, and that's the arithmetic average. Then there's the median, that's the midpoint in the data set. And then there's the mode, and that's the number that occurs most frequently. And looking at these three quote unquote averages, you can see they're pretty different figures. Which average would you like to use on your tax reporting? So to really understand the data, we need more information. Specifically, we need to know the spread of the data, and that's the range. What was the lowest? What was the highest? And quite often you'll see that just shown in a histogram. This histogram shows the number of smart people, ages 10 to 90, that attend spray demos. Not that I have any vested interest, of course. Is it typical for 90-year-olds to attend spray demos? Well, you can see very few do, but typical is a fluffy word. When the mean and the median are the same number, you have a special situation called a normal curve. You may also know it as a bell curve. And that curve is symmetrical. And when that happens, we can talk about variability using something called a standard deviation. Your standard deviation is just a way to determine how far a data point is from the mean. One standard deviation means 68% of all the data fall within a certain range. 2 standard deviations means 95% of the data fall within a certain range. So using standard deviations, now when we look at the 90-year-olds that attend spray demos, we can see they fall more than 2 standard deviations away from the mean. They make up less than 2.5% of the overall data set. So we can conclude there aren't too many coming out to spray demos. If we collapse that histogram, that data set, we can show it a little differently. We can now show the mean with some measure of variability. We could use standard deviations, but there are others like standard error. The point is, without some indication of variability, you really can't talk about a data set. You certainly can't compare two data sets. And I know it's like beating a dead horse, but without variability, you don't know anything about your data. Now, we described a normalized curve. It's not always what happens. Often data sets are skewed. For example, in this graph, here's the effect of a new herbicide on quackgrass. When data is skewed, that means the mean and standard deviations can't help us anymore. Honestly, the best way to show a range of data isn't with a histogram or a curve. The best way is with a box and whisker, and you may actually have seen this graph. It relies on 5 numbers: the minimum number, the first quatrile, the median, the third quatrile, and the maximum. And you can see here that each of these numbers represent a quarter of all the numbers in the data set. The minimum to the first quatrile is 25% of your data, and so on. The box in the middle represents 50% of the data, and the whiskers represent each 25%. And you may even end up with an outlier, which is one of those occasional wacky pieces of data that fall well outside a normal range for one reason or another. Sometimes they're statistical errors, and sometimes they could be relevant. The point is, a box and whisker is really the best way to compare data sets. It gives us variability, it gives us range, and it allows us to compare it more easily. John Allen Paulos, professor of mathematics. 79.48% of all statistics are made up on the spot. Yeah, I thought it was funny. Let's keep going. Here's another sample study. Researchers want to know which of 3 fertilizers produce the highest wheat yield in kilograms. So they design a study. They have 3 treatments. They have 5 replications for each treatment. Perhaps it looks something like this. Variables like soil type, other local influences like water, may have unexpected impacts. You can see that all the 1s are right next to the water and all the 3s are next to a wooded area. Could either of those create a confounding variable that are going to affect our experiment? Very likely. So a good study is randomized, and that defeats potentially confounding variables. We scramble them. Once they're scrambled, what we're hoping is that the sample plot in our study represents all the wheat in all the world. Do you think that might be the case? Well, with all the unknown variables that might influence it, there's always going to be a degree of uncertainty. Maybe our sample represents the world, maybe it doesn't. And that's why the more samples we have, the more confident we are that our study represents the population, that it's repeatable. You can determine how confident you might be using a confidence interval. And anyone might be used. Sometimes you see 99, sometimes you see 80, but 95% is often chosen. So when you see a confidence interval, that means that 95% of the time you expect your data represents reality. So beware any reporting that doesn't have a confidence interval. Tables are another preferred way to show data over graphs, but graphs paint a seductive, quick, easy to understand picture. Sometimes maybe too quick. Perhaps the presenter wants you to see a relationship between 2 variables. In this case, fertilizer 3 appears to really increase the average yield of wheat. But what kind of average is this? Mean, median, mode? How big was the sample size? Where is the indication of variability? Are they 80% confident this is going to be repeatable or less? And where is that confidence interval? So let's just add a few error bars. Really changes the story, doesn't it? Bad stats and bad experimental design often lead to bad conclusions. Correlation does not imply causation. I'm hoping you've heard this before. If not, here's a good example of it. The more firemen fighting a fire, the bigger the fire is observed to be. Therefore, more firemen cause an increase in the size of a fire. It's a great make work project. Probably not true though, right? Correlation does not imply causation. A presenter may want to lead you to a conclusion. Newspapers, television, certainly the internet should be scrutinized. Beware the following statements. This is not a scientific poll. These results may not be representative of the population. Based on a list of those that responded, and data showed a trend but was not statistically significant. Now, I confess I've used that one. So how do we show data in a way that actually makes sense? First, forget pies. Pies are for eating or maybe throwing. Some organizations of data in graphs make it really hard to see differences. We call this chart junk, and beware of it. Sometimes it's just amusing graphics. They're just distractions. You want to see, if anything, a graph with no adornment so you can truly understand what's being shown. It makes it hard to see differences if you're being distracted. Also, beware the scale. This is the same population growth data. We just use two different scales. Which would you use if you were hoping to demonstrate rapid growth? Beware tricky scales. Also, beware statements with no context. Here's a made-up example. It's no worse than any other factoid that I've heard over the years. Maybe someone tells you, did you know that even speaking to someone that once sprayed pesticide doubles your chance of getting cancer? That's alarming. That's really concerning. But without context, you don't realize that your odds go from infinitesimal to slightly less infinitesimal. We started this by saying that descriptive statistics are tools, and any tool like stats or a hammer can be misused, sometimes intentionally, sometimes unintentionally. If you take anything away from this talk, it's to maintain a healthy skepticism. It's okay to question a presenter, question their charts, question their tables, and question their conclusions where you feel there's insufficient information provided. I know I'm a horror at talks when graphs come up and there are no error bars. There are no counts of N or how many samples they took. There is no indication of how confident they are in the results or the conclusions they're drawing. So we'll end with this. 3 statisticians were hunting. They came across a big buck. The first statistician fired, but missed by a meter to the left. The second statistician fired, but missed by a meter to the right. And the third statistician threw down his rifle and cheered, "We got it." A lot of the information in this talk came from the Cartoon Guide to Statistics, which is a fantastic book, and a very old one, but still relevant, How to Lie with Statistics. Anyone interested in learning more about spraying, particularly in horticulture, we're happy to announce the second edition now available of Air Blast 101. It's available in print at cost or free as an ebook. And of course, a reminder to go to Sprayers 101 for all your spraying information.